There we go. Fancy. Okay. Yeah, so yeah, I've been tutoring for ages. I graduated from UCL. I did 4 years there. So I did like bachelor's and master's, and it was really fun. Loved it.
Glad they
And
come up.
since then, I've just been teaching people basically. But through the years of me teaching a lot of people,
Hello.
oh, hello, hello, hi, did someone say something? Yeah, through the years of me teaching loads of people, I basically realized that everyone's basically struggling with the same stuff. And it's more to do with like the approach that people take to learning chemistry than like any particular points. So the purpose of me putting on this little thing today, I'm not going to be able to go through every single reaction. I'm not going to be able to go through like every single example, the exact differences between everything. But what I'm trying to give you guys is kind of like an approach and a way that you should sort of be looking at chemistry or organic chemistry in particular. And yeah, like a way that you should be thinking about things so that you can take that with you when you're going to do revision, when you're looking at questions, and use that to make sure that you do as best as you can in your exams, basically. So I got a couple of questions in my little thing. How long is this? I actually don't know. I would say probably like an hour and a half, but I'm a bit chatty, so it might last a bit longer. And I don't want to just go before I've like covered the things that I wanted to cover. But I definitely won't keep you lot more than like 2 hours. I've got things to do and I'm a bit hungry. So yeah, probably like an hour and a half. Um, Okay, and also asking for like specific functional groups. I'm basically gonna touch on all of them and then go through examples. So as I said, I'm trying to give you guys kind of like a methodology of how you should tackle organic chemistry in general, mainly like organic synthesis. Um, and so we're gonna look at like all of the functional groups, but rather than looking at them in terms of, oh, this is alcohols, this is alkenes, I'm going to get you guys to look at them in terms of this is what's important to know about a functional group in general, this functional group in general. How does that influence its reactivity, and how is that going to enable you guys to figure out what kind of reactions they're going to do? So we will sort of look at every single functional group. Mm, but I'm not going to like do every reaction or every group. So let me start. The first thing I wanted to show you lot
Not
today
to go live.
was
Oh yes.
let me move this out the way. This.
There's 75 serious guys. All of us could bag A-stars.
So let me put a little screen share. I nicked this. How many of you, I don't know if you lot are gonna like talk back to me, but how many of you use CGP revision guides? Lots, yes, no, maybe. Them banging little books. I used to get them for GCSE and they're just really, really good. Like they're great. So I stole this from one of the CGP revision guides. Oh, more people are joining us. So what this is, I've just put on the screen for you, is like a table that summarizes all of the functional groups that you're going to encounter in organic chemistry in your A level. And the reason why I wanted to draw your attention to this is because it makes some important, like it draws your attention to some important points. I think from my experience, obviously I can't talk for anyone, but the thing that everyone kind of seems to be doing wrong as such when they're approaching chemistry, not just organic, but chemistry full stop, is kind of panicking because you've got an exam thinking, oh, is this going to be in my test or not? And trying to remember everything. And you can't, like, it's just not possible. You need to understand what's going on instead. And so a lot of the time in school, you'll
Mom
get
is calling you.
stuff.
Yes, mom.
Oh. You'll get introduced to stuff and you'll think, oh, what's this? I need to memorize this instead of actually understanding what's going on and how that's going to influence what it does. So yeah, what I wanted you guys to look at is obviously, yes, there's all of these functional groups. You can look at this in your own time. I'm not going to read through every single one with you, but look at what it is that they're pointing out about each functional group. They're pointing out the properties, and when they're looking at properties, what they're looking for is things like polarity and lone pairs and electron-rich double bonds or like electron deficient, like delta plus, like carbons. And realistically, when it comes to organic chemistry, understanding polarity is what you need to understand the topic full stop. And rather than, like I said, I don't want you to memorize the answer. I don't want you to memorize the reactions. I want you to understand how the reactions work. So making note and thinking about the properties of every different functional group, you can see then next to properties, there's a little column that says typical reactions. The typical reactions make loads of sense when you've looked at the properties. So we can go through some of them. First one, for example, alkane, non-polar, unreactive. It's not on anything. Look at typical reaction, radical substitution. That is, as the name suggests, radical. It's a bit extreme. You've got to do a lot. Like, it's not a simple reaction. You have to put a lot of energy into it. If you look at some of the other ones, another like completely opposite example, acyl chloride, you've got a carbon with a double bond to an oxygen and a double bond to a chlorine, both electronegative, really electron deficient carbon center, and acyl chlorides literally react with anything. Don't have to heat them up, don't have to add a catalyst. So much of this like organic chemistry that you have to remember for your exam, you don't actually have to remember, you just have to understand. And then it becomes so much easier. And it's kind of just like a fun little puzzle game. All right. Let me go back and look at what you lot have been saying. You lot, wow, loads of you don't use CGP books. Go and buy them, get them. There's like an online version, so you can literally pay for it and get it instantly. They're cheap and they're banging. They tell you everything that you need to know, but they're not long-winded. They're like the language is easy to understand. They've got pictures. Yeah, if you don't use them, definitely use them, especially at this point where you're like getting close to your exams. If you get stuck on something and you want to go and find out the answer, you don't want to read a big chapter of a book to get the information. CGP revision guide, banging, you'll read like 2 pages tops and you'll find what you need. Year 12 and year 13, yeah, I'm gonna basically do organic chemistry year 12 and 13. So if you're in year 12, sorry, a lot of this you're not going to know about yet, but it will still be useful for you going forward, unless you're planning to drop chemistry, which I don't approve of. What else have you lot been saying? Use it as a last resort. Nah, CGP is number 1, literally. OCRA, is it OCRA? All right, and yeah, good questions, guys. Good note about or a note for me about exam boards. Basically, across the exam boards, I would say 90 to 95% of it is the same. The only difference is the order that you get taught it, the way that they group it together, and some of the examples. So like transition metals, everyone learns like different metals, but the theory is the same. It's just you've got different metals to learn and different colors to learn as an example. So I'm going to try and keep this widely as general as possible. Like I said, I'm not trying to go through every single reaction and the entire specification. I'm trying to equip you guys with the correct methodology, the right thought process, and the right strategy so that you can apply this and understand organic chemistry. That way, you'll actually be able to work the problems out for yourself and get marks in your exam. Anyway, so yeah, as I was saying, looking at the different functional groups, the main things that you really want to focus on are the properties, or is it polar, does it have lone pairs, and typical type of reactions that it does will link into those properties. So that was just something I wanted you guys to look at. This is in the CGP book. I'm sure you can probably find it in like other books as well. If you look for it, or if you really want it, like send me a message and I'll email it to you. That's useful. The other thing that I wanted to show you guys, let me open this and put like another screen share, is another one that I nicked from a CGP book, which is reaction types. So it goes through basically the types of reaction that you're going to see in your A-level chemistry. And again, rather than trying to memorize the 30 plus reactions that you're going to cover in your A-level, it makes a lot more sense trying to understand the 7 types of reaction that you actually have. If you understand that, rather than, yeah, having to like, you know, memorize and regurgitate these answers, you're actually going to be able to work out and understand what's going on for yourself. So I would definitely recommend taking that approach. Also, like as like a, I don't know, disclaimer, I'm saying this to you lot because I made the mistake. Like when I was doing my A levels, when I was in uni, until I finished like the full 4 years of me being at uni studying chemistry, I was basically doing it wrong. Like I was in that state of panic of, oh my days, I've got an exam. Is this going to be in my exam? I need to remember it. Instead of oh, actually, why don't I try and actually understand what I'm being taught and then use that knowledge to solve the problem? So I'm saying this from experience. I wasted a lot of time copying things out and trying to memorize things and do past papers and do things in exam conditions when actually I didn't know what was happening. I didn't put enough effort into understanding what's going on. So yeah, I'm saying this like don't make the same mistakes that I did. All right, cool. So reaction types, another thing that you've got to kind of think about. You'll be surprised how many people like don't, let me not say like don't get this, but you just have to think. That's all you've got to do in chemistry. Like apply yourself. Don't panic. Don't bug out. Just look at what's going on and and think about it. So things like different types of reactions. The names are pretty self-explanatory. Addition is when you add things together. Elimination is when you get rid of something. Substitution, swapping something. Condensation, when a small molecule condenses out of your reaction. Hydrolysis. Um, Hydro means water, lysis is like cutting, so splitting something apart using water, and then oxidation and reduction. I'm sure you remember oil rig. So these are the main type of reactions that you're going to come across. And obviously you've got your whole electrophilic, nucleophilic that you can attach to some of these as well. Just learn the definitions, or again, think about the wording electrophilic, electro like electron, philic like. So if it's electrophilic, it likes things that are negative. If it's nucleophilic, nucleo like nucleus, positive, philic like it likes positively charged things. You can save yourself a lot of pain and a lot of heartache by like, let me not say learning a bit of like Latin, but thinking about like why things have got the name that they've got in chemistry. We don't name stuff for no reason. Normally the name kind of tells you what's going on. So I've showed you guys these two kind of things. And these are the things that you kind of like, you have to have this understanding in your arsenal before you can really hope to find yourself like successfully tackling organic chemistry questions. The next things I'm going to show you is I would say probably the most important tool that you're going to have, which is synthesis map. Now, as I said earlier, I'm trying to equip you guys with some skills on how you're going to manage to like tackle organic chemistry and organic synthesis in general. And what I'm saying here kind of applies to chemistry full stop and like across the board, education across the board, specifically sciences. So what I was banging on about, oh, you need to understand what's going on instead of memorizing it applies for everything. And so one of the things that really helped me is kind of using like a, I don't know how many steps, but like a process. Every time I come across an organic chemistry question, I have like a certain process that I would follow. Obviously, the process I'm going to tell you, you can't do when you're in an exam because it involves checking stuff. But if you follow this process while you're revising on the kind of lead up to your exams, by the time you get to your exam, you naturally would have sort of memorized what's going on. And also you'll have an understanding of what's happening rather than feeling like you need to just memorize what's going on. So synthesis map is the key, for me, was the key to basically bettering myself when it comes to being an organic chemist. So before I show you the synthesis maps, I'm going to talk to you about the steps that we're going to take today when we're looking at different reactions and how you're going to use that to solve these problems. Like I said, initially, when you're revising, you're going to be doing this using help. So as you might have seen me saying in some of my videos, I do not encourage that you do anything with a closed book until maybe like the couple days before your exam. Even the day before your exam, I would still say using an open book to find information that you can then go and apply correctly is more beneficial for your learning than doing it in exam conditions and just writing down something that's wrong. So I always advocate for using the information that's available until the very last minute. So the strategy is look at the question, identify functional groups, there's a table with functional groups on it. So if you're really struggling that much, get the table out and use that to help you, yeah? Once you've identified the functional groups, the questions are going to take one of a few different forms. Either it's going to say one functional group plus some stuff makes something, and it's your job to work out what that something is. Or it's going to say one functional group can turn into another functional group when you add something else, and it's your job to figure out what that something else is. Or it's going to say this thing can get made from something and another functional group, and you have to guess what that functional group is. So once you've got your synthesis map, and once you can, what have I done? Once you can identify functional groups and use those to basically navigate your way around your synthesis map, it's a piece of cake from there, really. It's kind of like, I don't know how many of you lot live in London, but when you want to get on the tube, you like, oh, I'm at this station. I need to get to that station. Oh no, I can either go directly from this line or take this line to here and then change and get that line. It's literally that, but chemical reactions and functional groups instead of train stations. So you're going to do that over and over again, and you're going to check over and over again until eventually you're going to find yourself going to look at the synthesis map, and before you've even looked, you know what it says. Practice makes perfect, yeah? Another key important step that I didn't do for a very, very long time is I was just kind of like accepting what I'm told. So I'll be like, all right, cool. Ooh, I need to turn an alkene to an alcohol. What do I add? Check my synthesis map. It says this. All right, I'm going to remember that. Don't stop there. That's where you're kind of like, yeah, you're doing yourself a disservice. Don't stop at that point. What you should do once you've found the information is think about the information for a little while and try to understand it. What I mean by that is, do you know the mechanism for that reaction? And whether the question asks for it or not, draw it. Draw the mechanism of everything all the time. Get a bit of scrap paper, write it on the side. If you're like, don't want to mess up your work, get a whiteboard. This is why I bought this when I was literally like first term of year one at university. I was like, yeah, I'm gonna waste a lot of paper. Draw the mechanism for everything, like everything all the time. And through doing the mechanisms, and I'm gonna go through the mechanisms with you guys in a minute. The mechanisms, again, don't settle for, oh, I'm going to remember the arrows in this picture. Think about why the arrows go the way that they do. And it always makes loads of logical sense. Chemistry is simple. Positive things go towards negative things. And that is what happens every single time in every single mechanism. So the more that you can try to develop your understanding of not just what is going to happen, but how it happens and why it happens, this mystery of organic chemistry, instead of it being, oh my days, I need to memorize 35 reactions, it's actually, oh, I need to understand 6 mechanisms, and it's not that bad. So I think that's probably the next thing that we'll talk about, mechanisms. So for this one, I think I'm just going to put up a little whiteboard. Oh no, not like that. Hold on. I don't want that kind of whiteboard. I want this kind of whiteboard. Oh, why is it giving me this? This is not the normal kind of whiteboard that I use, but I guess it will do. So what I wanted to do next is just talk to you about the, no, this is actually jarring me. Hold on. Ugh, no. Just give me a normal whiteboard. What's happening? All right, I was trying to find like a normal whiteboard, but now this is a different type, and all of you lots of little curses are popping around. It's doing loads. But what I wanted to do next is talk to you guys about mechanisms, because mechanisms are basically the key to understanding organic chemistry. So, like I said, we're trying to move away from feeling like you're memorizing what's going on and move towards feeling like you understand what's going on, and that way you can predict what would happen when you're presented with like a different situation, or yeah, something different happens to what you've seen in your book. So whoa, where did my whiteboard go? Why? Technical problems are the bane of my life. I don't want this kind of weird whiteboard. Hold on.
You can remove the access from us.
Can I? How do I do that? Sorry, I'm not used to like zoom in lots of people. I'm used to zoom in like one person at a time, and then I'm just in charge.
Naomi,
Yeah.
the people on your TikTok are complaining that it's
Why
not showing.
they can't see me?
Yeah.
Oh my days. I need to do some like, I don't know, like technical maintenance. All right, hold on.
Oh, one for me as well. One for me as well.
What is it?
Check it.
Both of them.
How do I, all right, who's like technology, who's like tech savvy? How do I stop you lot from messing with my whiteboard? Hold on. Aha, advanced
Can you
share.
see that? Oh, can you see those two people at the top?
The two people at the top.
Like the two. Can you see that? Or is it just me?
Hold on.
Yeah.
What, like some option more? Preferences?
All those three lines.
Yeah. Okay.
And at the right side, there's the two people.
Lock board? No. Do you know what? I've got another plan.
What if,
Hold on.
because you mirrored your screen when you were doing the PowerPoint,
Pardon?
were you mirroring your screen earlier when you were
Yeah,
doing?
normally what I do, if I just press share screen and I click whiteboard, it literally just brings up a white blank screen that I can draw on. It doesn't bring up like a fancy like Zoom whiteboard. It just brings up like a normal, like literally it's a blank screen that I can write on. But don't worry. I can.
There was
Why don't you try it on
thing.
Paint
There
or
was like
something?
there was
Yeah,
three
I'm gonna
lines.
find a way
It said-
around it.
It said
I'll find-
preferences, and then they had an option for no grid when you went on the whiteboard.
No, but
So
it's
it
not
gets
about
rid of
just the grid. It's like the whole format of the whiteboard is just different. Like, yeah, preparing your whiteboard experience. That's not the type of whiteboard that I want. I just want like a plain whiteboard. But I can find, hold on. I've had these problems before in my lessons. Ooh. I will just find another one. Furthermore, I have a document with all of these mechanisms in it. I'm acting like I haven't actually made it. Let me just show you that instead. All right.
People are also saying they're in the waiting room as well.
Okay, 1 second. There you go. I can just show you this. I've done it already. Waiting room. I feel like my meeting is about to be full. I need to, this is a lot, you know. Yeah, my meeting's full. I can't let any more people in. I also need to sort out my TikTok. Oh Lord. It's overwhelming. Your line has been into okay, hold on. All right, one of you lot needs to be like my eyes and ears on TikTok and see if did my live like do what it's meant to do. Anyone?
Not yet.
No, it's supposed to be screen sharing on my TikTok. So you should be able to see like what you lot can see on Zoom, they should be able to see.
It's blank.
This is black.
Yeah.
No, why? That's not fair. Someone's saying they can see it.
Yeah, we can see it. It's on there.
It's working. It's
Work.
working.
Okay,
Yes,
yay! I'm so happy. I was proper last night, like on YouTube, doing everything. Like, how the hell am I supposed to make it? I was thinking, I don't want to just put my phone here and like record the screen. That's not going to be good enough. Yay, good. All right, perfect. So, right, mechanism stuff. So basically, let me make this small for a minute. I yesterday was thinking about like what stuff I wanted to cover and how I can go over this and make it not like 5 hours long. So I drew out all of the mechanisms, just like an example of each one. And what I wanted to talk to you about is like what's actually happening in the mechanism and why it happens, and kind of like getting your head around that, because a lot of the time I feel like, sorry, it's really noisy. Yeah, a lot of the time, again, I don't want to speak for you lot, but I'm just saying, in my experience, students that I've encountered that have like hired me to tutor them, they're just like trying to memorize it instead of thinking about what actually goes on. And they'll say, like, I'll ask them a question, they'll give me an answer, right or wrong. I'll ask them, all right, then why does that happen? And they're like, I don't know. That's not good enough. That's not what, you can't get away with that in chemistry. So I'm going to go through each of the different mechanisms that you're going to learn, and we'll talk about in each example, like kind of what's going on.
Sorry, it stopped working again.
Oh my days, why? It looks like it should be, as far as I can see.
Yeah, it's working now.
Yeah? All right, I don't know. It's being a bit dodgy. What is... Right, hopefully it works. Fingers crossed. If it doesn't work for my TikTok live people, the whole thing is getting recorded. So if you really, really want it, I can get it to you somehow. I'll make it happen. All right, anyway, let's talk about mechanisms. So ideally, I think I might actually just draw them out from scratch. I think it's easier to understand a mechanism when you see it happening step by step rather than just looking at the completed picture. So what I'm actually going to do is cover up what's already here and then draw it out for you again. So first mechanism that I've got might not be the first one that you come across or that you came across when you were learning, might not be the same for everyone, but first one, nucleophilic substitution. So let's have a little think about what this means. Nucleophilic means a nucleophile is going to come in, and then substitution obviously means it's going to swap for something else. Now, we know that nucleophiles, we said that they're attracted to things that are like the nucleus, so they're attracted to positive charges. So in order for a nucleophilic substitution to take place, you obviously need to have something that is a nucleophile that is attracted to positive charges and itself would have either a lone pair or negative charge. And you would also need to have something that is positive or partially positively charged for the nucleophile to come and attack. So the example that I had written out before was, where's my little pen? We had a haloalkane, so something like this. Every time we go through functional groups, the thing I want you to think about, like I said before, is properties. So think about polarity, lone pairs, partial charges, all of that jazz. From here, the thing that's popping, the thing that's like, oh yeah, that's exciting, where it's going to react, is the hydrogen and the chlorine. That is a polar bond. Chlorine, electronegative. Sorry, not hydrogen, carbon and chlorine. Chlorine is electronegative, so it's going to be delta minus. Carbon is therefore getting its electrons basically stolen, and it's going to be delta plus. This is the perfect time for us to introduce a nucleophile. So as we said, nucleophiles are attracted to positive charges and themselves will have a negative charge or a lone pair of electrons. And so if you're a chemist like me that like has a, you know, bit of experience and thinks about how chemistry happens, the next part is incredibly obvious. And if you start looking at mechanisms in this way, it will start to become incredibly obvious for you guys as well. So quite clearly, we have one part of this entire molecule that's more positive than everywhere else, and then something else that has a negative charge. So obviously, those two things are going to react together. Remember your sort of ground, like basic rules for mechanisms. So your curly arrow shows the movement of two electrons, a pair of electrons. Therefore, curly arrow has always got to start from a place where there is two electrons. So either lone pair, negative charge, or a bond. So I often see people doing this. Don't do that. It's not going to go towards something that's negative. So make sure that you're always drawing your curly arrows going in the right direction. Again, just a little bit of thought, thinking about what the arrow represents will save you from doing it in the wrong direction every single time. The amount of times I've been working with someone, they've drawn the arrow in the wrong direction. I said, oh, why did you draw it that way? And they say, oh, should have drawn it the other way. Do the thinking before you make the mistake. Quite like, it sounds obvious, but yeah, do the thinking first before you make the mistake. So we're going to get an arrow. What color should I make it? Let's make it pink. And it's going to go from the lone pair of electrons on the oxygen towards the delta positive carbon. Then you know enough about chemistry. Carbon can only have 4 bonds at once. So obviously, if that new bond, it's gone a bit far, 2 electrons getting shared, this is meant to be shells, is a covalent bond. So when those 2 electrons from oxygen go to the delta positive carbon, we're making a bond with oxygen and carbon. And then we're going to break the bond between carbon and chlorine because the carbon can't have 5 bonds at a time. So going to do that. Now I can see some questions coming in. What's going on down here? Ooh, what's that? Hold on. Does it matter what side you draw the lone pair on and the negative sign, as long as the arrow comes from them? Well, kind of, yes. One thing to get your head around is that chemists, we're like, as much as I know it's kind of annoying, like we're really picky about stuff, like it's actually good because it means everyone knows what's going on all the time. So should we draw the negative charge on, we can't draw it on the other side because the hydrogen's not negative. Hydrogen doesn't have a lone pair. Oxygen's the one that's negative. Oxygen's got the lone pair. So you have to draw it on the side of the oxygen. It seems trivial, but actually you just have to be accurate. So little things like that, I feel like it's easy to make that mistake, but once someone explains it to you and you understand that there's actually a reason behind it, then it's like, oh, okay, yeah, fair enough. I get that. Won't do that again. So yeah, does matter which side you draw it on. What else? Aromatic mechanisms are hard. I'm going to show you that. There's only one. I can't even, there's one aromatic mechanism, and other bits are like other mechanisms you've seen in other places, just with benzene slapped in there. So I'll sort that out for you as well. What else? How much do I charge tuition? £50 an hour if you're interested, guys. I wanted to put on some like group classes as well. And I think like, you know, like if you guys have got like a group of, I don't know, like 4 of you or 5 of you and you want to have a lesson, I'm going to do that. But to be honest, I'm not like, as I'm sure you can tell, I'm not the most tech savvy. So I've just been like cruising through, doing my little one-to-ones, but I want to reach more people and help more people. So over the next few weeks, I'm going to try and find some like actual solutions as to how I can help more people and actually, yeah, get more of you to understand what's going on. Use my whiteboard behind me. You must be joking. No way. My actual whiteboard. I haven't used that in a while, to be honest. It's just for display now. I used to be like super hands-on, but obviously since COVID, I had to start tutoring people online, and now I'm like, nah, stuck in my ways. Like I like Zoom. That's what it's all about. So anyway, I'm going to keep like periodically checking in with the comments and stuff. So if you've got questions and things, feel free to put them in there. But yeah, that's our first mechanism, nucleophilic substitution. Hopefully, now that I've kind of broken it down for you. Oh, wait, hold on. I'm capping. It's not done. I haven't even drawn the product. All right, cool. So as you can see, we're making a bond between oxygen and carbon, breaking the bond between the carbon and the chlorine. So the result of that is going to be our, well, these things haven't changed. Nothing's happened over there. Oh, goodness me. Get rid of that. Nothing's happened over there. But we have replaced this chlorine with an OH. And then the Cl, because it's taken both of the electrons from this from this single bond. Remember, when carbon and chlorine formed that single bond, they donated 1 electron each to make that covalent bond. Chlorine has now taken back its electron and the electron from carbon, so it's going to leave as a Cl minus, and there's the end of your mechanism. So that's the first one done. Quite straightforward mechanism, I think. Well, it is once you've kind of broken it down and thought about why it happens and how it happens, rather than just trying to memorize what happens. And like I said, I feel like that's kind of the downfall of everyone, is too much memorizing and not enough actual understanding and not enough thinking. So yeah, that's the first one done for us. Next one we're going to look at is electrophilic addition. So I reckon I'll probably just do the same thing again, and I'll cover up, we can have a look at it over here, but I'm going to cover it up and draw it sort of step by step, because I think that way it's a little bit easier to like understand what's happening, rather than just having like this one picture. You're going to see the step-by-step changes as they occur. So find it hard to remember. So I keep getting distracted by you lot's comments. Find it hard to remember conditions. You're not the only one. Everyone does. Everyone actually does. Yeah, memorize that mind map thing. Basically, yeah, it's hard to remember conditions, but once you have a better understanding of the mechanisms, rather than feeling like you have to memorize the reagents, you're going to understand why a certain reagent is an appropriate choice for a reaction. You would also understand things like, oh, this is a very reactive functional group compared to this one. This one I might have to catalyze, this one I wouldn't, this one I'll heat up, this one I won't. So even when it comes down to conditions, yes, there is definitely an element of memory to it, but it's not all memory. And everything that, like, the best way I can put it, every bit of information that you get given, just keep asking yourself why. Like, why? Like, why would I have to use this? Why would, you know, this thing react with this thing? Why does it attack here? Just keep asking yourself why. And there is always a reason. Or if there isn't, it's just going to minimize the amount of things that you have to just like straight up memorize. So, right, I'm going to draw this out, but let me cover up. I can see I'm getting a couple of questions about this mechanism. So hold on, let me draw it. Does it say, why does it still have a negative charge? I've just seen that. It's not supposed to be that. It's not supposed to be there. That's just my sloppy diagram drawing. So let me cover it up and draw it properly of how it's actually supposed to look. So there we go. All right, electrophilic addition. Again, thinking about the wording, electrophilic, it means that we're going to have an electrophile. Electrophiles like electrons or negatively charged things, which means they themselves will be either fully positively charged or have a partial positive charge. Let me let some people in here. Oh, I feel like my Zoom is just not behaving in its usual way today. All right, admit you lot into the waiting room. Anyway, yeah. So we're going to have an electrophile, and if in doubt, H2SO4, big facts. Yeah, an electrophile reacting with something that is going to have an area of negative charge or a lot of negative charge. And then, as we said, it's an addition. So if you are doing names of the mechanisms, that one, I'm like, how can you find it hard to remember the names of the mechanisms? The names of the mechanisms tell you what's going on. So if you know what's happening in the mechanism, the name is just a description of what's happening. So look, let's use this one as an example. So electrophilic addition. At the end, I'm going to come back to it and we're going to talk about why it is an electrophilic addition. So as we saw in my example, we had an alkene. So let's draw this alkene. And then I put hydrogen bromide next to it. So you're going to start getting used to the kind of pattern that I'm about to show you, which is look at the things that you've got reacting together and look for lone pairs and look for partial charges. So that's what I'm going to do first. So with regards to the molecules that we've got here, there's no lone pairs or partial charges on an alkene, but referring back to that table, the kind of properties or the characteristic special things about an alkene is the fact that it's got a double bond in the middle, 4 electrons all in one place. So loads of electron density in the double bond of the alkene. And that explains why and how it does the things that it does. I will move on to the harder mechanisms eventually, but I'm going to go through all of them. Why? Are you in some kind of rush? Want to go? All right. Yeah, so looking at what we've got here, loads of electron density in the double bond, nothing like, but other than that, nothing else is going on. Then between the hydrogen and the bromine, we know that hydrogen's delta positive, bromine's delta minus. Other times you might see this with like Br2 and it's still polarized. The reason it will be polarized is because of the electron density in that double bond of the alkene. It kind of like scares the electrons away from the atom that's closest to it, and it would cause even a Br2 to become polarized in the same way. So using the understanding that we have of mechanisms and positives and negatives. The most negative bit on this whole thing is the C double bond. The most positive bit is the delta positive hydrogen. So the electrons are going to go, as always, from the most negative bit to the most positive bit. So that's going to be us creating a bond between the hydrogen and the carbon. At the same time, as you know, hydrogen can only form one bond at a time. So the hydrogen-bromine bond is going to have to break, and we're going to end up with our picture. Now, this is a good one, actually. There's two options. You could either add the hydrogen to the left-hand side, or you can have the hydrogen to the right-hand side. Markovnikov selectivity rule, knowing which is major and minor product, is what we're about to discuss here. So you will add the hydrogen, if you want to make the major product, you're going to add the hydrogen to the side that will result in having a more stable carbocation. So what I'm going to do, I'm going to go draw this a bit smaller, and I'll draw both possibilities for you. So we could have this one, or we could have this one. So you can see I've added hydrogen to the left in the top one, and I've added it to the right in the bottom one. One of these is going to be more stable than the other, and stability depends on the carbocation and the stability of the carbocation. So the more carbons that the positive carbon is joined to, the more stable it is. So if we look at this one at the top, we can see that it's bonded to 2 other carbons. If you look at the one at the bottom, it's only bonded to 1 carbon. So the one at the top would be more stable. The way I think about this, having a charge, being an ion, is not something that carbon wants. It doesn't want to be positively charged. So it's a stressful and difficult situation for carbon. It's a peak time for carbon right now. The more friends it has to help it, the more support it's got, the wider its support network, the more brethren it's got, can share the stress with its friends, and it makes its life a bit easier. So carbon at the top's got 2 solid, good friends that are helping him through this difficult time, and he's all right, he's relatively stable. Carbon at the bottom is going through it, and he's only got 1 brethren at his peak. He is not stable. He's not nice. So that's kind of like the way that you can think about it. If you're struggling to remember, that's a way that it makes sense. Guys, can you mute your mic, please? Right. I'm trying to, this is like a lecture. Yeah, get you lot ready for when you're at uni. You don't participate, you just listen and then type your comments if you want to talk. So yeah, we've got more stable intermediate at the top, less stable intermediate at the bottom. And the selectivity rule says that the major product is formed via the more stable intermediate. So the more stable intermediate at the top, we would call that, somebody said, what's the actual wording to use when you explain it in the exam? So the one at the top, because the positive carbon has 2 other carbons connected, we would call this a secondary carbocation. The one at the bottom, because it's only got 1 other carbon, would be a primary carbocation, similar to like how you have primary and secondary alcohols, like same nomenclature. So what you would say is that the secondary carbocation is more stable than the primary, therefore the major product would be formed via this more stable intermediate. So that's the yeah, that's like the wording that you need to use. The thing about wording as well, in chemistry, a lot of definitions and a lot of stuff that you get presented with is like fancy wording that just sounds a bit like gobbledygook. Rather than looking at that stuff, you're going to get sick of me saying this, rather than looking and saying, oh, I need to remember that, it might be in my exam, spend some time actually thinking about the physical meaning of what it is. See if you can put it in layman's terms. You lot probably gathered by now, I'm from West London, I'm a slang speaking normal person, but somehow I managed to get a master's in chemistry because I understand it. I don't speak in my normal day-to-day life. I speak in slang and my grammar's horrible and I don't care, I quite like it. But when I need to, I can turn up because I actually understand what's going on. And if you understand what's going on, these definitions and these concepts and these mad questions you have to answer, all you're actually doing is explaining something that you already understand with the appropriate language. We can all turn it on when we need to. So yeah, definitions and all of that kind of stuff, even like looking at things in the mark scheme and like what you should write in your exam, strive to understand everything. Don't just settle for, all right, I'm going to remember that. Think about it, think about the meaning. And once you understand it, saying it properly is not that hard. All right, cool. So more stable intermediate, less stable intermediate, then products, or next kind of step of the reaction is that this Br minus that we would have created in the first step, and speaking about earlier, because the bromine, like last time, again, it entered into agreement with hydrogen. It said, yo, bro, let's put one
What?
electron.
Just because I didn't say yes the first time.
Excuse me. Yeah, hydrogen and bromine made an
Okay, just because I'm not going gym now.
Excuse me, can you mute your mic if you're going to talk about gym?
Boy, I'm online.
I go gym as well, but people are trying to learn. Yeah, hydrogen and bromine, they made an agreement, 1 electron each. Let's do this, bro. We'll chill together. And then bromine suddenly said, actually, I'm taking your electron and my electron. So bromine is now negative. So you end up with a Br minus ion. From there, it's quite obvious if you've got something that's negative, the Br minus is going to go towards this carbon that's got a literal positive charge on it. So your next arrow is going to be electrons from here to here. And I'll draw both possibilities like that. Products that you're going to make. How am I going to fit this in? Hold on. Let's see. You lot are all laughing, you know. Don't laugh at me. I feel like this is like training. So I've been a tutor for 7 years, as I keep saying, but I've never been like a teacher. Oh yeah, I could have drawn a lone pair on the BR. You could do, yeah, you can do. Can I repeat what I said about bromine? Okay, bromine and hydrogen made an agreement when they have like a covalent bond is like an agreement between two people, yeah? They said, cool, look, I'm going to put 1 electron in, you're going to put 1 electron in, and now we're both going to be more stable and we'll stick together. It's nice. You lot made, yeah, it's like a little plan. All of the sudden, hydrogen is accepting 2 electrons from somebody else. And he's like, do you know what, actually, bromine, I don't even need your electrons no more. I'm going over here. Gives the electron. So bromine is taking back its original electron that it put into the covalent bond and the electron that hydrogen put into the covalent bond. So that's why it ends up as Br minus, because it's Br plus that extra electron. So yeah. Where was I? Anyway, yeah, so you got your Br minus, and then products, let me find a place to draw them because I'm running out of space, or I might just have to do them really small. The product that you would get from the top one, you're going to have your H, C, C, H, CH3. So none of this is change, H, and then your bromine, that doesn't even look like a H. Your bromine's going to be on the right-hand side, the same carbon as the CH3. The bottom one is going to end up giving us, that's meant to be a CH3, sorry, it's disgusting. H, and then bromine on the left-hand side like that. So you can see this one at the top is going to be your major product because it's formed via the more stable intermediate, and the one at the bottom is the minor product because it's formed via the least stable intermediate. So what does more of the stable intermediate form in a reaction? So does more of the stable, yeah. So basically, it's not necessarily that more of the stable intermediate forms. I'm going to get a bit deep now to stuff that you don't need to really worry about. But the stable and the unstable intermediate would both form because there's like an equal chance of them forming. There's no reason why the hydrogen would go to one carbon than the other. However, the unstable intermediate is so unstable that oftentimes it doesn't exist long enough for the bromine to then come in and react with it. It goes backwards. So it's like an equilibrium, and it's far to the left. So it gets made, but it doesn't really stick around for very long, and it goes back. So every now and then you get to catch one and you make your minor product, but most of the time you don't. So wait, the most intermediate have more hydrogens. No, the least stable intermediate has more hydrogens. The more stable intermediate has more carbons. So think about the like order of the carbocation. Is it primary, secondary, or tertiary? Primary carbocations bonded to 3 other carbons are the most stable. All right, I'm going to keep it moving because this is actually taking a bit long. I haven't got...
you know you said the 2 carbons.
Mm-hmm.
Well, what if there's only 1 carbon on both?
Then 50-50.
Ah, okay, that's
So
fine.
they're equally as stable. None of them is going to be major or minor. You'll just get equal split of both products. Good question. Thank you for that.
Ah, okay, thank you.
Cheers. All right, next one, elimination reaction. This one's kind of interesting. Depending on what exam board you're doing, there will be differences, slight differences in how you're kind of expected to draw your mechanisms, or sort of like what reagents you use. I can't remember if it's year 1 or year 2. That's one thing I will say to you lot as well. I'm just a chemist. I'm not gonna lie. Like, obviously, yeah, I tutor, so I see like, oh, this is in this exam board, that's in that exam board. But as far as I'm concerned, it's all the same. Just understand chemistry and you'll be straight. It doesn't matter which exam board you will be. It's your job to kind of like check up the intricacies and check the details. It's my job to make you understand and approach it in the right way. As I said, every student I've ever encountered in the last 7 years, the problem has been their approach towards chemistry. There's nothing wrong with their brain. Like, it's not that they can't remember things or they can't do maths. It's that they're just doing it wrong. Your approach is often wrong. So I'm here to fix that for you guys, which is what I wish someone done for me. So yeah, elimination mechanism. The reason I'm bringing this up about differences in exam boards is because you can see in my mechanism, this H is just kind of coming off on its own. In different exam boards, it might be different things that make that H come off. So some of them don't mind if it just comes off in its own. Others might give you like, I'm drawing it a bit dodgy, but others might give you this that comes and steals the H, and then that's what makes it come off. So just rate determining step. I'm sorry, boo, but this is not the place for that today. I have done a video on it on my TikTok. I'm gonna do more of these classes as well. They might not be free though. I'm not gonna lie. I might make you look pay a little £5 or something. But I'm gonna do more. So not just organic. I'll probably do one. I'm gonna do one on transition metals, definitely, because everyone keeps asking me about it. But it's too long to fit into like a TikTok video. But yeah, I'll do some inorganic, organic, physical, whatever. Try and rescue lot before exam season actually starts. But cool, yeah. So some of them might show it kind of getting taken by something. So I've left. What do you mean violating £5? Do you know how cheap that is compared to what people normally pay me, brother? Yeah, anyway, so I'm just gonna draw it coming off on its own. Beg you free. Listen, you lot have got parents, tell them to run it up. Tell them to run it up. This is my job. I'm dairy free. I don't eat Freddos, so I don't want no chocolate. I want money. No, I also just want to help people, to be honest. That's why I feel like £5 is reasonable. I might lower it, but I feel like that's a good starting point for like 2 hours of my time. That's wild for a £5. That's less than minimum wage, cuz. Run up, ask your parents. I feel like it's good value for money, isn't it? Anyway, so back to this mechanism, elimination. Let me draw it out from scratch. But yeah, I'm just going to draw the hydrogen dropping off. Check, I've got bare chemistry tattoos. I'll do a video about that one day if you want. Yeah, I'm going to show the hydrogen just coming off, but check for your specific exam board, yeah? Think about the followers I'll gain. I'm trying to, don't worry you lot, man. I'm coming. Anyway, pause, no diddy. I'm gonna show you this mechanism and I'm gonna do the next one, a lie. I'm gonna show you this mechanism and I'm not gonna show what comes to grab the hydrogen. Go and check in your specific exam board what comes to get the hydrogen. I'm not gonna tell you because I don't want it to be like for one exam board anyway. Do the next one, man. I'm doing it. Cool. Elimination. Simple. So we'll think about what actually happens in an elimination reaction. So we're gonna have an alcohol. Like this, and in an elimination reaction, something is going to cause this to happen. But like I said, I'm not going to tell you what, because you're going to all have like slight differences in your exam boards. But something's going to come and grab this hydrogen, or it's just going to drop off on its own. So what you're going to see is hydrogens, electrons. So the electrons from carbon-hydrogen bond going down and donating to the carbon-carbon. So that's going to turn it to a double. And then the carbon-oxygen breaks and the OH is getting kicked off as an OH minus. So that's your elimination mechanism. It's quite an easy one. If you think about what's come off, you've gotten rid of a H plus and an OH minus. So you're going to end up making an alkene and water. So a dehydration, elimination, however you want to call it. So get rid of that. That one's quite easy. Next one, nucleophilic addition elimination. This is like, as far as I'm concerned, the mechanism of like A-level chemistry. So many of the reactions that you learn, make some practice papers and sell them. Now you're talking. Yeah, that's a good idea. It's a bit long though. I can't bother to invent questions, but maybe. Yes, H3PO4, H2SO4, oftentimes that's what it is. Yeah, concentrated acid or whatever. But right, perfect. See what I'm saying though? Understanding of the mechanism, you're thinking to yourself, all right, what could it be that would grab a proton? It would be that negative ion that's left behind. Or how can the proton just come off on its own? If it's in acidic conditions, it can just exist as a H+. So do you want to screenshot this? Yeah, of course. Yeah. Do you know what I'm going to do? I was doing this earlier. I'll try and finish it today. Have I got more lessons? I've got lessons later in the evening. I'm going to put some little like link tree. I feel like it was special. I'm going to put link tree in my TikTok, and then on there you can click on stuff and like download this and like synthesis maps. Might even make you pay for them though. So like synthesis maps, mechanism summaries, and like resources and stuff. But yeah, people, I was going to say that, you know, obviously I want you lot to learn chemistry, but if the playing field is not level, it's not fair, the papers get leaked. So check like the night before, because sometimes it does happen. Is the arrow on the elimination H going to the C or the CC bond? Put it to the CC bond, because that's where it's going. Does it act as a base or a nucleophile first? Do the amine one. All right, cool. Anyway, let me get, addition elimination. This is, as I said, like the mechanism of A-level chemistry. So many of the reactions that you learn are taking place via this mechanism. So have a think about what it's called. Also, sorry. I was meant to talk about the electrophilic addition and the naming thing. So the name of the mechanism, we got an electrophile, and we added it. So this was the electrophile, and then we didn't get rid of something, so we didn't eliminate, we didn't substitute, we added. So the name is always basically based on what is happening. Anyway, nucleophilic addition elimination is a great mechanism. So think about the name, nucleophilic, so you're going to get a nucleophile, addition, elimination. So there's going to be 2 steps. You're going to add, and then you're going to eliminate. It's really simple. Like, I don't know, maybe it's just because I've been doing this for a long time that to me it's just like glaringly obvious. But some of this stuff, honestly, I think people struggle with it just because they're in panic and they're like, oh my days, I need to know all of this stuff, rather than just like, let me think about this. So nucleophilic addition elimination, I'm going to show it with an acyl chloride, because these are the most reactive and popping things that you see reacting. And I'm going to put ammonia as my nucleophile. So as per usual, first thing you want to do, draw out the molecules and look at the like polarity, lone pairs, partial charges, all of that jazz. So have a look. Ammonia, nitrogen, it's got a lone pair. Acyl chloride, we've got delta positive carbon. Anytime carbon is double bonded to an O, it's delta positive. Every single carbonyl group that you see, so aldehyde, ketone, carboxylic acid, ester, acyl chloride, acid anhydride, is there any more? Amide, all of them, that is what makes everything happen. That's it. The whole thing is because of that delta positive carbon. So clearly that's what's going to react. And our nucleophile's got a lone pair of electrons, so it's negative. So obviously the NH3 that's negative, there's only one bit on the whole molecule that's positive is going to get attracted there. So let's draw our little electrons going here. So we're drawing the 2 electrons representing bond being made between nitrogen and carbon. Then the carbon oxygen double bond, carbon can't have 5 bonds at a time, so it's going to break and turn into a single. In our next picture, what we're going to see is this. So now our nitrogen is bonded. But now nitrogen has 4 bonds, so it is positively charged. So you can see I've got N and then, oh no, N and then a plus charge. And then our oxygen has got a negative charge. This is still polar. So what's going to happen in the next picture is the electrons from this oxygen is going to go back down to reform. So we did the nucleophilic addition in the first bit. We added on the NH3. Now we're doing the elimination. So the oxygen is going to reform its double bond with the carbon. And then because this carbon-chlorine bond is polar, chlorine's already delta minus. It doesn't really mind becoming completely minus. So that just drops off. It's a good leaving group. At the same time, one of these hydrogens is going to give the electrons from its bond back to nitrogen to help it get rid of its positive charge. And our final product is going to look, I'm like running out of space, it's going to look like this. Then we'll have NH2 and then HCl. So this H and this Cl fill link up and form a HCl at the end. Hopefully that makes sense. But as I said, there are so many examples of this mechanism at play in the reactions that you look at. So there's like, what have we got? We've got formation of esters, this is how it happens. Formation of amides, this is how it happens. Formation of carboxylic acids, this is how it happens. There's so many reactions that take place via this mechanism. So if you, yes, that is an amide. If you get to sort of understand this, then you should be fine. Is it not supposed to be a double bond on O? You reform the double bonds in the middle, you don't have one. But yeah, so you can see, again, thinking about the naming, we got a nucleophile, we did an addition, and then we eliminated. The next mechanism that we're going to look at, what have I got? I think it's an electrophilic addition. What's this? Let's go down. That's not an electrophilic addition. That's a nucleophilic addition. See what I'm saying? I was making this yesterday. It was lazily and badly labeled. This is a nucleophilic addition. Let me cross that out from now so you don't get confused. And the reason I wanted to do this mechanism next, or I put them next to each other, is because it's really similar to the one that we had before. As you can see, the first step is basically the same. So you've got something with a carbonyl group, and then the CN minus, so a nucleophile, comes and attacks, and then the CO double bond breaks. In this one, it's in acidic conditions. So instead of it just becoming O minus, it goes and grabs onto a hydrogen and you get the OH as a result. How long left do you reckon? I don't know. I feel like I'm taking long, so I'm going to try and speed up a little bit. But yeah, that's that mechanism. Nucleophilic addition, not electrophilic. And then what else have we got? Finally, electrophilic substitution. So this is your mechanism that you get with benzene and aromatic molecules. So this one, again, all stems down to understanding benzene. Benzene has a ring of delocalized electrons, and so all of its reactivity goes back to that. So the delocalized electrons make benzene really stable, so it's difficult to make it react. And it doesn't want to lose that ring of delocalized electrons. So instead of doing addition reactions, it would always do like a substitution reaction instead. So you can see it reacts with electrophiles, obviously, because it's negatively charged. It's got lots of electron density. And so the ring of delocalized electrons in the middle gets attracted to the electrophile. Then this hydrogen that was always there, I just drew it in the next picture, donates the electrons from its covalent bond back in to reform the ring, and you've done a substitution. Was HCl a product of the addition elimination? Yes, it was, because we got rid of the Cl and a H came off the NH3 part. But yeah, this is kind of like mechanisms, like very, very brief summary. So the final thing that I needed to show you before I actually do questions, and I'm going to try and finish up kind of soon because I know you lot don't want to be here all day. But hopefully, as I said, I can't teach you the whole of organic chemistry in like an hour and a half. All I can do is teach you like how you should be thinking about things and why it should make sense. Can you please explain again why the electrophilic addition, the Br, is negative? In an electrophilic addition, why the Br is negative? Let's have a look. Why the B? Oh, because it's connected to a hydrogen. I was just trying to remember what I'd put in the picture. It's connected to a hydrogen, and bromine is more electronegative than hydrogen. But I said earlier, even if the two of them, yes, reactants and conditions is coming. Even if the two of them were both bromines, the bromine that's closest to the double bond in the alkene obviously the double bond is lots, like it's got loads of electrons, so it's electron rich. So all of the electrons on the alkene, or sorry, the atom that's closest to the alkene's double bond gets scared away, and it's like, oh, and it runs away. And so whenever you have, whether it's HBr or Br and another Br, whichever one's closest to the double bond would be delta positive, and the one on the other side would be delta negative, because all the electrons have kind of run away to that side. You lot are proper conspiring to buy papers, innit? Rah. I'm not gonna lie, I'd be on that as well. Like if I'd studied for all this time and then there's other people out there that are just gonna buy the papers, I'd be mad. But I'm not gonna lie, buying a chemistry paper is not actually that useful, because even you get the paper like the day before, you get like the day before the exam, the paper will get leaked, and unless you stay awake all night trying to memorize that paper, it's not really going to help you that much. I feel like you still need to have a level of understanding. No, buy the papers and share that, man. Do your thing. Level the playing field. If other men have got the papers, you lot decide to have the papers. You deserve to have them too. But yeah, I was going to say, like, you can't I doubt you can memorize all of the answers for the entire paper if you only get it the night before. And like, you still need to have some level of understanding to like get through it. So it's kind of worthwhile. Like if your last resort, like you're getting U's and you just need to scrape something, buy the paper. But I don't know, it will take the pressure off, I feel like, but you still have to find the answers to all of the questions the night before and then memorize them. So it's not that like, yes, it's not that helpful. Anyway, right, mechanism thing I wanted to show you was the next little job. So as I said earlier, the kind of strategy that you're going to use and the thing that you should kind of be thinking and doing is look at your organic chemistry question. And then once you've looked at your organic chemistry question, identify the functional groups that are in the question, then check your synthesis map. Check the synthesis map. The synthesis map will have the answer. Once you've looked at the answer on the synthesis map, don't just stop there and say, all right, fine, yeah, I accept that. Go on and try to understand it, draw the mechanism, and yeah, just try to make sense of the chemistry. That's the most important thing that I can say. Like, understand chemistry. You can't memorize it all. It's literally impossible. So I feel like I opened these all like a million times. All right, cool. So let's do, I'm going to show you a lot of synthesis maps for AQA, EdXL, and OCR. To be honest, you're going to see what I was talking about as well, about how they're mad similar. Like there's not that much difference between them, but I'll show you all of them quickly so you can have a look. And then we're going to do like a couple of questions using, like breaking it down and using the strategy that I've been talking about, which is literally, as I said, like identify functional groups, check synthesis map, blah, 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 blah. And as I said earlier, like, I don't recommend that you do this closed book until maybe the night before the exam. There's no need. It's better that you look for the answer, find the answer and use it than just try and like, oh, I'm just going to guess. Don't guess. It's a waste of time. It's a complete waste of time. So yeah, let me put my little screen share and show you guys this synthesis map. This honestly, oh, go on, sorry.
Sorry, do you have the WJC one?
But I can find you one or I can make you one. To be honest, I took this synthesis map from a book, but you'll see my one is way more turned up than any synthesis map you've ever seen, because I color-coded the arrows by mechanism. So instead of just feeling like, oh, I need to remember this, there's actually a level of understanding to it. And I also drew out the structures instead of just saying the name of the functional group. Now, these are minor changes, but I feel like it makes all of the difference. So what are you lot saying in my little chat? Adam Snap, will I do inorganic? Yeah, I will. Can you send us this map after? I might do. I'm thinking I might send it to you lot. Pardon?
Can you zoom out a little screenshot, please? Just for like 1 second.
What do you mean zoom out and screenshot? This is my product, huh? I might, you'll see it. I might give it to you lot that are in my Zoom, and then everyone else that didn't come to my Zoom will have to pay. We'll see. But yeah, let me just get through what I need to get through quickly. or I'll make it like a free download for the next 24 hours. And after that, how much do you reckon I should charge for a synthesis map? What, like £3? Anyone?
Free.
Free? Like FREE? £5. See, that's what I'm saying. Run it up. You lot don't understand, you know, it's a hard life being a tutor for the whole summer. No one ain't studying. I'm unemployed for like 3 months. I got rent to pay. Yeah, trying to make some money out here. But anyway, our synthesis map, or my synthesis map, is better than all the other ones. 60p, yeah, fair enough. £1, yeah, this took me a little bit of time, you know. My one's better because I drew the structures and I color coded it via mechanism. So this is going to help your understanding. Like I said, I don't want you to just check the synthesis map and say, oh, all right, perfect, yeah. I'm just going to remember that. I want you to check the synthesis map for the information and then try to understand that information. Chemistry is not about memorizing things. Chemistry is about understanding things and using them to solve problems. So it's okay if you need to check stuff, but then understand that or try to understand that. And then next time you're not going to need to check because you're going to understand. So what you're going to do, look at the questions, look at this synthesis map, look at where it says, I've color coded it. Look, this is an electrophilic addition. So if you have a question where that happens on a bit of paper, try and write it out. Write out the mechanism. It might be useful for you. And the more times that you do it, eventually you're going to find yourself coming to look back at this synthesis map. And before you even look, you already know what it says because you've looked at it so many times. But practice makes perfect. Just get questions and open the map and use the map to answer the questions. Use the map to answer the questions over and over and over again. Don't worry about memorizing it. Memory comes last and speed comes last. But like, if you can't do something with an open book, how are you ever going to do it closed book and quickly? It doesn't make sense. So use this first and then scroll, let us see quick. Yeah, don't worry, I got you lot. Look, so this is the top half, yeah? Here's the bottom half. I don't know if I can fit it. Look, screenshot. It's me giving away my product. Yeah, there's the bottom half. And then I made this one for Aromatic. Hopefully you can see it's a bit smaller. Look, I'll even zoom in for you lot. Don't say that I'm not a nice person. Yeah, you all finished, yeah? Do you sell a document? That's what I'm about to... Listen, don't worry. I'm about to make like a store. I'll pay that. That's what... Yeah, don't worry. I'll do it. 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 Selling them for £5. Don't try to rip off my materials. That's one step too far. Come on, man. Flashcards, no. I don't really believe in flashcards. Well, let me not say I don't believe in them. I never use them. All right, cool. So here's, yeah, this is your AQA synthesis map. So you can see what it looks like. As I said before, there's bare reactions on here. Let me zoom out a bit. Like, I'm not trying to stop you lot from whatever, but like, look how many reactions there are. Look how many arrows there are. There's a lot going on here. Rather than trying to memorize everything that's happened, look how many colors there is, about 5 or 6. Understand the mechanisms, don't try to memorize the reactions. That's the best thing. All right, let me show you next exam board. Who's next? OCR. Let me do, that's OCR question. OCR synthesis map, here you go. So you'll see, as I said before, it's like 99 to 95% the same. So this is OCR synthesis map. Zoom out a little bit first. Again, as you can see, bare reactions, hella arrows, lot going on, but not that many different colors, not that many mechanisms to it. Like, look how many of them are blue. Blue is nucleophilic addition elimination. Enough reactions are blue. If you understand that mechanism, you don't have to memorize any of that. You just have to understand it and then apply it at the right time. This is like the secret, yeah, of chemistry. Like, understand it, don't memorize it. If you understand it, it's light work. So, all right, for all you OCRs, if there's any of you out there that want to come and rip off my product, yeah, this is the top half of OCR. I am going to do a question, yes. So yeah, this top half, bottom half, hopefully you can see all of that, or you can like get it all. And then I'll give you a few seconds so that you can rip off my organic bit. There you go. Oh, top half of organic. You've got a question? You've got a question, like an actual exam question that you want to send me, or just like a question that you want to ask? Let me know. Please go back to AQA, maybe in a little bit. Oh, I've got an idea. Sorry, guys, I live in like quite a busy area, and I can hear mad commotion. It sounds like someone's scrapping outside. What's going on? I think, does an aldehyde reflux? You lot are doing a lot. Hold on. All right, look, before I leave this meeting, I'm going to be nice. I'm pretty sure there's a way that I can put documents into this chat. So I'm just going to upload the transition. What the fuck am I talking about? The synthesis maps to the chat. So stop asking me for them. I'm going to send them to you. Okay, I'll boss you lot, but you lot, I'm going to say you're obviously going to share with your friends. I don't know. I need to find some new customers that will actually pay for that stuff, because I need to make some bread. All right. Except my boy, he's trying to join. Admit all. There you go. Oh, I've lost some of you lot. We're no longer at capacity. All right, cool. All right, anything else? Leave your bank deals and I'll transfer. Pattern influence. I literally need to. I'm trying to make it out the hood. I'm literally trying to make it out the hood. Does an aldehyde reflux or distill to a carboxylic acid? All right, Farhan, yeah. Use your brain and you'll be able to work it out for yourself. When you reflux something, you put your condenser upright. So the stuff reacts, it goes up as vapors, and then it condenses and it falls back down again. So which one do you think it makes? If you oxidize an alcohol once, it turns to an aldehyde. So your aldehyde vapors go up, then your aldehyde drops back down, it gets oxidized again, and it turns to a carboxylic acid. When you distill something, you put it sideways. So it reacts, your aldehyde gets made, and it goes away straight away. So it doesn't get to do it again. That should make sense. That should make a lot of sense, hopefully. Yeah, anyhow. All right, so showed you that one. The last one, EdXL. Is there even any EdXL students in this joint? Because I feel like there's just none anywhere. No one does EdXL. I don't know why. It's actually a decent exam board. I quite like it. There is, yay! I think it's a good exam board. They're not easy on you lot though. They're not easy on you lot. OCR is goated. OCRA is goated. OCRA is the best exam board, and it has the best like marking. It's just the best. OCR, if you do OCRA, you're ready. Like, you can be a scientist. You're prepared. You can go to university and you know what's going on. Like, your head works. If you do AQA, you're all right, but they're just nasty to you lot. They're so picky. Like, oh, you didn't say this word, so you're not getting the marks. OCR is like, if you're telling the truth, you get the marks. So OCR definitely, like, EdXL's good, but they're challenging. They push you lot. OCRB is just on crack. Like, I don't understand. The content is the same as everyone else's, but they've just grouped it together in storylines about the ocean and colors instead of like organic, inorganic, and physical. It's a bit of a mad thing, but it works, I guess. I mean, it's kind of interesting, and it connects the curriculum, which is nice depending on what you like. But for me, it's a pain. Like, they've got like the topic name oceans. I don't know what's in there. Just talk to me. Like, I want to know what everything is. So yeah, OCRB, you're not finished. It's long for you. Everyone else, you're good to go. All right. So this is EdXL synthesis map. Catching up on what you lot said. OCR isn't easy. 90% for an A star. That's fair though. Come on. You want to call yourself A star and you can't get 90% on a paper. You don't deserve one. I'm mean, I'm horrible. But do you know what it is? OCR, it says OCR isn't easy, but it's a lot easier to get 90% on an OCR paper, I feel like, than an AQA, because the OCR paper, like, they actually give you marks if you say things that are true. AQA are like, oh, but you have to say it like this, you have to do it like that. So I don't really like it that much. All right, anyway, here's your EdXL synthesis map. Looks incredibly similar to the others. This one looks a bit funky, actually. I quite like that. So yeah, there's the top half. It's been on there for a while. Here's the bottom half. And I'll show you, warning though, I forgot to do the one for phenol. So I think it's Edexcel or it might be OCR. One of you lot learn about phenol, and I haven't added it on. I forgot to do it, but I have made it. So I'll add that on at another time at some point. All right, let's do some questions. Finally. I'm going to start on AQA. I'll see if you lot don't mind. I don't mind. I'll try and do one from every exam board. But to be perfectly honest with you, like I said, 90 to 95% of it is the same. And I always say to my students, like, just ignore the exam board, do questions from wherever you like it's not that deep. It's chemistry, it's chemistry. Post the document, please. I will before I go. I can't do it right now. So question, let me put my screen share on this question and show you how to do it. So here is a question. This is an AQA question. I took it from the world famous physics and maths tutor. So it's like some pack of organic synthesis questions, and it's the first one. As I said to you before, synthesis questions come in all shapes and sizes. Sometimes you know what you're starting with, you know what you're trying to make, and you've got to fill in the middle part. Sometimes you know the starting material and the reagents, or sometimes you know products and reagents, and you just have to fill it in. But strategy, identify functional groups, check your synthesis map, try to make sense of what's going on, repeat. So in this question, it says that we're trying to make a diester from cyclohexanol. So here is cyclohexanol. And then we do something to it and turn it into that, then do something else to it, it turns into compound G, do something else to it, it turns into cyclohexane 1,2-diol, then we do something else to it and we get this diester. And to be honest, I don't really care what the question says. The question is going to ask us like, ooh, for step 1, what's this? For step 2, what's this? Da, da, da. I just want us to try and fill in all of the missing information. Like I said before, or I've said in my videos, I'm not too fussed about like, well, obviously I'll tell you a lot about how to answer the questions, but my job is more to get you lot to understand what's going on. If you fully understand the process, whether they ask you about step 4 or step 2 doesn't matter, because you understand what's going on. So I'm going to try and basically just ignore what it says in the question and get you to think about the whole thing. So without further ado, let me make some space. And I feel like you lot have been pretty good at like not talking over each other. Do you not want to contribute? Do you want to help me to solve this problem? Or would you prefer me to just show you how to do it? Anyone? All right, I'm just going to show you how to do it. So as I said, don't care what the question says. I just want to fill in all of the gaps. So start with step 1. First thing you want to do, identify functional groups. The functional group on the thing that we're starting with in step 1 is an alcohol. The functional group that we're trying to go to is an alkene. If you don't know that, check that table. At all points, like at any point, you should never be guessing. You should never just be, oh, I'm just going to do this because I just think. No, never guess anything. If you're not sure, just go and check. Go and check, make sure you know, and then move on to the next step. So cool, we know that we're going from alcohol to alkene. The next thing you want to do, it's really, really simple, is just look at your synthesis map. So where is it? Here it is. I'm going to have to change my share to a new share. So annoying. I need to hire one of you to be like my tech support and just do all of this stuff for me. So look at your synthesis map. I know this seems like a cop-out, and don't be scared because your exams are soon. You don't have a synthesis map in your exams. I know it seems like counterintuitive to just check everything, but trust me, this is what you need to do. So yeah, we know that we're trying to go from alcohol to alkene. And look, there's an arrow that connects alcohol to alkene, and it says concentrated sulfuric or phosphoric acid. So we've got an idea of how that happens. I'm going to go back now to my question. Where is it? Here it is. And so I could fill in this reagent. So I'm going to go with sulfuric acid. Then the next thing that you want to do, again, I know that the exam question is not asking for this, but I don't care what the exam question says. I'm trying to make you to understand what's going on. And this is the approach that you should kind of have yourself as well. Extend, do you know when, like, when you're doing like GCSE maths and you get that question, like bare sheet, like sheet with bare questions on it, and then there'll be at the bottom and it's like extension. And if you're a bad boy, you do the extension, you're like, yeah, miss, like handled mine. extension yourself, extend yourself all the time. Try to understand what's going on. I don't like, it sounds a bit obvious, yeah. The reason that you have to do an exam is not because the people at OCR don't know the answers to these questions. We know the answers to the question. The reason you're doing an exam is so that you have a chance to demonstrate your understanding. So do that and develop an understanding. Don't just focus on the answer to the exam question. The exam question is just a tool that we use to see, have they actually understood this stuff or not? So push yourself, do a little bit extra, and it will pay off. So the little bit extra that we're going to do is think about the mechanism of this reaction. We've seen it already today. It's an elimination. So this is another really important step, is once you've identified the reaction that happens, or once you've identified the mechanism, draw it out and then try to, man said, Miss, hurry up, you know, I told you I love to chat. I'm proper talkative, seriously. Anything else that's important? Easter was yesterday, yeah, I know. All right, whatever, let me just carry on. So yeah, the thing that you want to do is, do I talk this much when I tutor? Yeah, I blatantly do. But it depends on the mood that I'm in. Today I'm feeling like a bit energized and talkative. I normally teach one kid in Riyadh at 5 a.m, but he's on holiday, so I didn't have to wake up bare early, so I'm all happy. But anyway, think about the mechanism for this reaction so we know it. Stop telling me to hurry up, Mohammed Hussein. I'll kick you out of my fucking Zoom meeting. So this is what we've got. So what we're going to do is think about the mechanism that we had before, and then man said violating £50 an hour for tuition, and no, but obviously normally I don't have 100 people sending me dumb messages when I'm trying to teach. It's one-on-one. Got people like you just chatting away, distracting me. Do you know what I'm going to do? I'm just going to close the chat, and then all of the questions are not going to get answered, if that's what you don't want me to do. Anyway, so we know this mechanism. Some kind of acid is going to come along and the H plus is going to drop off, boom, like this. This is going to come off, and then reaction, easy. Now, I know that they don't ask you for this in the question, but if you do this, this is how you're going to understand, yeah? This is how you're going to be able to understand what's going on. And instead of feel like you need to memorize things every single time, you're actually going to get it. So cool. We've established what's happened over there. Step 2, compound G, we don't know what that is. Step 3, cyclohexane 1,2-diol. So this one's a little bit different. We know that we need to make a diol out of something. Now, kind of easy considering you've got a synthesis map. And on your synthesis map, if I show you, I know it feels like we're cheating, but I promise you we're not. There's only one way to make a diol. You have to make it from a dihaloalkane. So, okay, cool. Clearly, you're going to have to turn your alkene to a dihaloalkane and then turn it into a diol. So we know how to do that. We add X2, Br2, Cl2 here, and then KOH, heat and reflux. So you've got it. Write it in. It's that simple. Like, I know I feel like I'm cheating because I'm just checking on the synthesis map, but realistically, that's what you're supposed to do until you memorize it. The important, or one of the other important kind of steps is, like I said, drawing in the mechanism. So step 2, we know that our compound G, if I get my little pen, yeah, we know that our compound G is going to be a dihaloalkane. So let's put Cl like that. And again, think about the mechanism. We know this one, it's an electrophilic addition. So you should be able to draw that out. Step 3, how are we going to go from this to this? Well, we looked at our mechanisms. Something I was going to say, actually, depending on your kind of like level of skill and level of experience with organic chemistry, I'd kind of recommend 2 different ways of doing this. So if you are kind of just starting out, or if you're still finding it really, really difficult, I'd recommend identify your functional groups, then check your synthesis map, find out what the reaction is, what the mechanism is, and then use that to get the answer. If you do not, or sorry, if you're a bit more advanced in your chemistry and you're kind of doing a little bit better, then I would recommend identify the functional groups, think about the polarity and think about the reactivity first, and then go and look at your synthesis map. So someone like me, I know about chemistry. I'll tell you the truth as well. I can't remember all those reactions on the synthesis map. Are you crazy? I've got way too many other things going on in my head. I can't remember them. I do not know them, and I'll tell you that for free. But what I do know is chemistry. I understand polarity. I understand electronegativity. I understand all these other things. So when you give me a question, I don't have to memorize the answer. I just look at it and I work it out. That's what you're trying to be like. You want to be like me. You want to work things out. You don't just want to memorize things. So yeah, we're looking at this one. So imagine you're a bit more of a savvy chemist. You're like, all right, cool. At the moment, I've effectively, let me draw. So you've got this going on at the moment. And then that's obviously connected and makes the rest of the ring, whatever. And we know, okay, well, chlorine is electronegative, so that would be delta minus, and carbon is delta plus. I'm trying to replace this with an OH. So I need some sort of reagent that's going to provide me with OHs, and I want them to be negative because I want them to come and attack this delta plus. So, all right, what could I use to generate OH minus ions? Maybe I could use a base like potassium hydroxide or sodium hydroxide. See what I'm saying? You don't have to memorize reagents, you have to work them out. And then understand the mechanism. Oh, it's going to come and attack here and kick this off. So like I said to you, instead of feeling like you need to memorize all this information, just have to understand it instead. So we know that we can go from compound G to our next compound, nucleophilic substitution, use potassium hydroxide or sodium hydroxide or something like that. Now, all of this, remember, I've done without looking at my synthesis map. So what you can do now is look at your synthesis map if you're sort of, you know, getting a bit better at chemistry, and check and see if you're correct. So like we said, look, add potassium hydroxide, heat it up, reflux it, reaction happens. So depending on, like I said, your level of experience, you can either go straight to the synthesis map, find the answer, and then try to make sense of it, or you can sort of use your knowledge to have a go and understand what's going to happen, and then go ahead and actually find out. All right, who's this trying to come in? You lot are actually bare-facedy. I sound so old, facedy. Rude little kids.
Sorry, do you repeat that twice? The OH.
Do I repeat the OH? Yeah, so well, again, this is just chemistry. You just don't need to be switched on. If you understand that mechanism, you will understand you can do it once or you can do it twice, depending. Look at what the question wants. In the question, they want it twice, so do it twice. If they wanted it once, do it once. So you just have to adapt. Like, don't feel like, oh, I need to memorize. This is what happens to make an alcohol. This is what happens to make a diol. Understand that it's the same mechanism both times. And so whether you do it once or whether you do it twice, that's going to be depending on your mole ratio. So how much do you put in and all of those kind of things. But like I said, try to think about it in terms of mechanism rather than she teaches me long-term investing. I used to want to be a dentist. That was actually like my goal when I was younger, but then biology's dead. I can't even lie. Oh my God. I got turned off by A-level biology. It was horrible. All right, cool. So I'm trying to hurry up because I told you I didn't want to keep you for like 2 hours. The next step 4, we're going from, again, identify functional groups. Alcohol at the top, diester or diol, double alcohol at the top, ester at the bottom. This one, again, if you've got a good idea of chemistry, you can kind of think about the reactions that you already know. If you're not too sure, what we can do instead is we can go and look at our synthesis map. So synthesis map says, if you want to make an ester, so go down to ester, it's down here. There's a couple ways you can make it, either using a carboxylic acid, an acyl chloride, or look, oh, an alcohol. We've got an alcohol, we want to make an ester. Clearly, we need to use a carboxylic acid. Then the sort of missing step, or the thing that a lot of people maybe don't do but should be doing, is trying to actually then apply that knowledge to the question that you've got in front of you. So think about the question that we've got in front of us. Let me draw a little blackboard, a little whiteboard. So think about the question that you've got in front of you. Your alcohol that you're starting with looks like this, and you know what this thing looks like at the end. So the new bond that you've made, or sort of the general reaction, is like this. So that's your general acid reaction. And then try to apply that to what you've got here. So you can see, okay, the new bond that I've formed is like this bond. And then this is like my alcohol. So all of this is essentially, or if you kind of split it up, do it one at a time, all of this is like the R of the alcohol, or R prime. And then this clearly used to be carboxylic acid. And so you can kind of work backwards in steps of what you've got and think back of how you could have made that. So for this one, we know that we would have wanted like the carboxylic acid version of this. So it would look like that. And you can figure out that must be your reagent for step 4. Esterification, you need sulfuric acid catalyst, so make sure that you've got sulfuric acid catalyst in there as well. Quite straightforward. So a question like this, if we now actually look at what it asks you in the question, reagents and conditions for step 1, reagents and equations for step 2, reagents and equations for step 3, mechanism names, complete the mechanism, suggest why they'd usually do this, talk about atom economy, blah, 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 blah. Obviously, from what we've spoken about, everything that's being asked in that question, you should answer because you've actually just considered it fully and understood what's fully going on. And realistically, that's all there is to it. That's it. You just need to try to understand and strive to understand what's going on in your organic chemistry. You can't memorize it all, there's too much. But take your time with it. A lot of the problem I think people have is that... Hello.
Can you hear me? Sorry,
Can
you go to the whiteboard screen for a second? I was just writing down the last mechanism that you wrote.
Oh, I don't know if I can get it back. I think it's gone forever, I'm not gonna lie. What was it?
It was RC double bond OH, and then you wrote plus R1.
Oh, yeah. Alcohol. I can do that.
Yeah. Thank you.
Where can I put it? I just got rid of the question. Hold on. I'm just gonna put it over here. I'll draw it for you again. Hold on. So that's another thing, actually. I'm glad you brought that up. That helps a lot is just looking at the overall transformation of a reaction. So if we had carboxylic acid like this, plus some kind of alcohol, knowing what they would make. Because essentially, this is what you're required to do as a chemist. But obviously, you're going to learn about the reaction that happens with a particular example in mind. And then eventually, what you're supposed to do is apply that to obviously other examples. So this is one. This is like the general reaction. So you can see I've specifically used R groups like on purpose so that it's not restricted to ethanoic acid and ethanol or like one particular example. The R group's literally anything. So any chain of stuff could be there. This is always going to happen as long as you've got carboxylic acid and alcohol with an acid catalyst. So the better you can kind of get that understanding and the faster you can almost like recognize the, what's the word I'm looking for? It's like for each mechanism, there's like a criteria that needs to be met in order for that mechanism to be able to happen. So for this one, nucleophilic addition elimination, you need to have a nucleophile, you need to have a carboxylic acid derivative that has a polar bond down here. So if you did aldehyde or ketone, it can't do addition elimination because there's nothing to eliminate. It has to do addition instead. So all of these kind of little tricks and things, as much as it seems like there's a lot to remember, it's actually not stuff that you need to remember. It's just stuff that you need to understand. All right, I'm going to get rid of this quickly and see if I can quickly do another one. That was an AQA question. Yeah, I'm going to find us. I found another like an OCR question that looked kind of juicy. Let's see if I can find it and we'll do that one quickly and then I'm going. This one. Oh yeah, there was a reason I like this one. This one was about paracetamol, and you lot obviously, do you do paracetamol, do you aspirin? You do some kind of making something as practical stuff. Always a good question to look at. So another example, of organic synthesis kind of question. So they've given you this structure of paracetamol, said that it's a painkiller. First thing they want you to do is identify functional groups that are present. Now, another thing I feel like a lot of people maybe don't pick up on is basically understanding or like realizing that when you have a question like question 6, part A, part B, part C, part D, they're all parts of question 6. So they're not going to get you to identify the functional groups in a molecule for no reason. So don't just do that and then forget about that and move on to the next part. They're doing that for a reason. They want you to, oh, okay, clock onto something and then use that as you continue on through the question. So yeah, showed us paracetamol, gets us to identify functional groups. I can see a benzene or a phenol, if you want to look at it like that. I've got an amide link over here because NC double bond O. So yeah, phenol group and an amide link. Already you should start thinking about reactivity of these things. So it says in the next part, chemist prepares a pure solid sample of paracetamol from 4-nitrophenol in 2 stages. So got a picture of 4-nitrophenol, we do something to it, we get an intermediate, we add some ethanol chloride to our intermediate and we end up with paracetamol. It's our job to basically fill in the gaps. So in the question, they ask you to describe a 2-step synthesis. They said that the overall yield is 40%. They want you to include the mass of 4-nitrophenol. So do a bit of amount of substance work. I'm not doing that now, it's long. But we'll talk about the stages and how you can kind of break down this question. And as I said before, it's really not that hard. Or it's not as hard as it initially seems. So the job here is figuring out the intermediate. What is that thing that we've got in the middle stage? So we know that we've got 4-nitrophenol, which starts off with, like we said, a nitro group and an OH group. And we can see that throughout this entire synthesis, the OH group hasn't reacted. So it's not doing anything. It's just kind of there. So the focus is clearly going to be the NO2 group. Now, somehow we've managed to go via the intermediate from an NO2 group to an NHC double bond O CH3. So clearly something's happened. There's been some kind of reaction. And we know that stage 2, so after we made the intermediate, we added an acyl chloride. So just thinking about this very like strategically, like not thinking about the specific chemistry as such, in terms of a strategy, you need to figure out, okay, what must this intermediate have looked like for it to have reacted with acyl chloride and formed that? We know a lot about acyl chlorides if you understand their reactivity. So let me draw it out. Acyl chloride, the one that they've given us, looks like this. So as we've seen many times before, carbon-carbon, delta positive, chlorine, delta negative, oxygen, delta negative, dumb reactive. This carbon is getting robbed of electron density from like all directions, super, super reactive, very easy to make it react with stuff. And so if you go and check your synthesis map, if you look at organic synthesis, or not organic, I was going to say aromatic or just regular synthesis, we'll see that acyl chlorides are susceptible to do that same nucleophilic addition elimination reaction. So we now know, okay, well, if that did react, I'm going to try and move this along. So put that over there. If this did react with a nucleophile, the nucleophile is going to come in, it's going to attack here, that bond is going to break. Then in the next step, the bond's going to reform and the chlorine's going to get kicked off. So we know that the sort of new bond that gets formed when you do a nucleophilic addition elimination with an acyl chloride is this bond here between the C with the double bond O and the nucleophile. So this Cl is getting swapped for something else. So we know that this must be the new bond that was formed, and that used to be some sort of nucleophile. Now, just from experience, I can probably say it's going to be an NH2, or it used to be an NH2. But if you're not sure, what you could do instead is look at what things can I turn NO2 into. You don't have unlimited options. As much as there is a lot to learn in A-level chemistry, there ain't that much. Yeah, it's not unlimited options. You only know 1 or 2, or like you only know a couple of reactions for each different thing. So it's not like rocket science to figure out which one is going to do which reaction. Where's my mechanisms gone? Let me find it. So if we have a little look at this synthesis map, you can see once you've turned benzene into nitrobenzene, there's only one thing that you can do to it. You can turn it into an NH2, and then you can react that NH2 with an acyl chloride and get one of these phenylamides that you've literally got in the question. So like I said, it's not that difficult. Just check your synthesis map. And then once you've done and checked the synthesis map, have a little think about how that would actually happen. So we're going to try and apply that to what we've got here. So let me do that quickly, and then I'm actually going to have to leave. So if we think about the reaction that we've got here, we're going to turn that thing into our intermediate. So if we draw our intermediate, it's going to have NH2 and HO like that. Now, if this intermediate was in the presence of the other reactant, so this thing here, we know what's going to happen. Nitrogen has a lone pair, it's going to attack, double bond's going to get broken. In the next step, it's going to reform, chlorine's going to get kicked off. And so what we'd end up with is we'd replace this chlorine for all of that. And that's what we have in our product. So you can see, again, I'm not stopping at just accepting what I've been told and just saying, oh, okay, I'll remember that for next time. Go the extra mile, draw out the mechanism, try to understand it. And I know this sounds a bit crazy. Like, I'll be honest with you, if I was you lot and I was like a few months away from my A-level exams and someone was telling me to slow down and take my time, I'm thinking, you smoking? Slow down. I've got exams. I'm panicking my way through this. But trust me, the more like extra work that you do around it to try and build a full understanding of what's going on, the less of this you have to remember. Like I said to you, I can't remember anything that it says on the synthesis map, but I understand chemistry. So I just work out what I need to work out. And there's a pattern, or like there's a series of steps that you have to take, or a series of questions that you can ask yourself, or things that you can look out for on different molecules. And if you do that, or sorry, different questions, if you do that every time, you'll always get the right answer. And instead of you having to memorize all of this stuff, you just have to think about or sort of memorize the way that you break down the problem. And honestly, that is like the most important thing. So yeah, like I said to you guys at the beginning, I'm not about to come and go through every single reaction with you and explain every single one of them to you. What I'm trying to equip you with is a technique, or like an approach that you can use so that you actually, instead of remembering all of this stuff, you actually develop an understanding of organic chemistry. And instead of feeling like you have to remember the answers to all of these questions, you can actually figure out the answers and solve the problems for yourself. All right, I haven't looked at this chat for a minute. I know you lot are doing absolutely loads. Bro, you're probably 70 kg. Who's getting into arguments? Aspirin, yeah, you lot do aspirin. You don't understand step 4. Miss, can you upload the thing? Mohammed, you're actually gassed, innit? Half you lot are fasting, chill, innit? NABH4 should be reduction. You can use NABH4, or you can use lithal. Lithal is NABH4's bad boy cousin. So if NABH4 can't reduce it, lithal will reduce it. What is a product like the thing you drew that's functional group is like an aldehyde, an ester? All right, yeah, boom. Step 1, you have got no hope in organic chemistry if you cannot recognize your functional groups. So that's the starting point. The starting point, though, just look in the book. So rather than getting a question, being like, oh, I think it's this, and just carrying on, don't do that. Just go and look, find out what it actually is, and then carry on. Yeah, Mohammed, you're actually bare rude. Say sorry to her. Yeah, lie. You lot are so funny. Yeah, thank you for backing me. All right, have you lot got any actual questions that are not just chatting crap for me before I go? Because yeah, I've got an actual lesson with a student in a little bit, so I want to relax for a little.
I just wanted to ask you to do the WJC map if you have access to it.
Yeah, I'll definitely do that. To be honest, all right. If you lot have never been, I'll give you lot some more free game. Have you lot ever been on ChemRevise? It's like this website. I'm not gonna lie, it doesn't look good. It's like, it's a bit dry, like everything black and white. Like it's a bit boring, but it's really, really good. And I think they've got WJC on Chem Revise. So if I can't find it, I will I'll make one. But basically I just copied that one, but drew on the functional groups and color-coded the arrows by mechanism. Also, I've got a really bad memory, so whoever you were that asked for that, can you just send it to me in a message on TikTok, like WJC synthesis map, because I might actually forget. Anything else? Where will I upload the documents? I'll sort it out. The chat meeting is moving mad. Alcohol.
By the way,
yeah.
you know the WJC inorganic side, or like, are you going to do inorganic live as well?
Probably at some point, yeah. Inorganic is long. I hate inorganic chemistry, I'm not gonna lie, but I probably will do because I want to save you lot. But like I said, next time there might have to be a little entry fee. I'm trying to run it up this summer. But yeah, I definitely will do. I feel like inorganic chemistry, it's just long. Like it's long. The topics take a long time to teach. Like they're just long. So I will do it because I don't think I'm gonna have much luck being able to explain it on like short videos on TikTok because yeah, it's just a bit difficult. But I will upload. All right, let me see if I can upload these documents. Have anyone got any actual like chemistry related questions before I leave? No. Physical is the best. Yes, physical chemistry is the best. Please, no entry fee. No, I'll see. Please do buffer calculations on TikTok. I've done it. I've done 3 parts. Fundamentals of chemistry like polarity. Yes. This is all really, really key. Like SN1 and SN2, I can do that. I haven't really put any transition metals or any organic stuff on TikTok at the moment. But I will eventually get to it. Meeting group chat. All right, how do I do this? I don't want to add a screenshot, a file from my computer. You lot are absolutely getting free game off me right now. Synthesis map. Also, let me apologize in advance if there is accidentally any mistakes in this stuff, but if you see some, then let me know, point it out. All right, there you go, look, I bossed you lot. I sent everything. So the 2 tables with functional groups and reaction types, I sent the synthesis maps for all 3 exam boards. And I also sent, Mohammed Hussein, you don't love me, you've been quoting me off all lesson. And I sent you that mechanism thing. All right. If you guys have no more chemistry related questions, I'm going to bring our little meeting to a close. It's been a pleasure. Thank you guys for thanking me so much. Obviously, at one point, I'm going to have to try and make money off teaching chemistry. But to be perfectly honest with you, the reason why I decided to come to TikTok and to put on this session and like to do this kind of stuff is because I am actually like a super, like you lot have seen it, I've got chemistry tattoos, like I'm a super nerdy chemist. I love chemistry so much. I think it's the best thing ever. And I just want to help more people to understand it because so many people think it's really difficult. And so many people are like, oh, you know, like, they just struggle with chemistry because I feel like they're taking the wrong approach and they're panicking and worrying about their exams instead of trying to actually understand. So yeah, I feel like I just want to help you lot understand this amazing subject and actually make the most out of all of the hard work because I see you students year in, year out, working hard and putting the time in and sometimes not getting the results that you deserve just because the approach is wrong. So that's what I'm really here for, like trying to sort things out and help people with their approach. I probably should have done this before, like not like 6 weeks before exam season. If I could have got to you lot at the beginning of year 12 would be ideal. But yeah, I'm trying to help you lot to really understand what's going on. That way you can actually solve problems, think for yourself instead of feel like you're just memorizing stuff. Who was that said that they want to send me a picture, a question? Send you a question on TikTok and make a video on how to answer it. Okay, right, before I go, let me put my email address in this little chat. And then if you lot, if you come across any questions, that is not my email address. that you get stuck on. I, of course, always want content and like ideas of new videos that I can post. So I will definitely, if you email me questions or send me questions, I will definitely answer them for you. What else? Geez, Mohammed and Debbie, come on. Ah, matchmaking. I feel like a catalyst. Yeah, if you guys have any questions at all, DM me or email me. I'll put on some more sessions. I'm definitely going to do one on transition metals because so many people have been asking about it, and I might do that one for free if I'm feeling nice. But yeah, keep a lookout for my like TikToks. I feel like a catalyst is crazy. You lot don't know. When I explain catalysts, I always say that they're like matchmakers because they take the two shy things that want to react together, but they just can't, and they force them to sit down with each other and chat, and then they move. Yeah, I've got a lot of them. I've got a lot of them. Miss, you're so fire. How tall are you? I'm only reading this because it's actually so funny. I'm the same size as like the average 12-year-old. Yay. Anyway, yeah, I'm gonna go. Phenol react. Oh yeah. All right. Sorry. Phenol reaction thing. Oh, I haven't actually done it. It's saved on like a Zoom whiteboard. It's not actually done. I've got the face of a tall person. I don't know how I feel about that. I don't know how I feel about that. The phenol one, I haven't actually finished doing it. I might be able to, hold on. If you don't mind, wait for it. You lot can cut if you're done. But I might be able to get it for you now before I leave this meeting. So it's just easy and you can.
Well, thank you so much, Miss. We appreciate it so much.
Oh no, it's all right. I know how it is. It wasn't that long ago that I was doing my own A-levels. It was. Oh, how old do you lot think I am? Give me some responses in the chat. That's an interesting question. 24, 26, 24, 23, 25, 24, 24, 23. Oh, I like this. This is great. No, I'm ancient. Yours is wrong. Keep going though. You're making me feel good about myself. I said 12. Yeah, that's the answer. That's my favorite answer. Miss is getting gassed. Thank you very much. 35. Don't violate me. I've got a master's degree, so I have to at least be above age to have gone to university for 4 years after. 31, got it on the head. Well done. Well done. Good work. All right. I think I can get you this phenol thing. Where did I put it? I don't even know where I put it. Hold on. It's on like a little whiteboard on Zoom. So I need to export the whiteboard and then I can send it to you. Ah, here it is. It's a bit of a mess. All right. Voila. Why can't I do anything? It's not letting me like do what I need to do right now. To hold on. All right, look, I'm just gonna have to. There, all right, hold on. Export as a PDF. Export area. Ha. This is really annoying me. Give me a second. I'm trying to figure this out. Hold on. It's right there. I just want this section. Okay, hold on. I'm just gonna have to do them separately. Oh, this thing is absolutely getting on my nerves. Okay, I'm sorry, but I can't get this for you right now because Zoom is making my life really, really difficult. Oh my goodness. That's why. Oh. Yeah, I can't do it right now. But you can find it really easily. I've got another plan. Hold on. Sorry, guys. Let's do it like this. I can definitely get it for you here. But it's not going to be as good as my one because it's not color coded. But it's close enough. So we wanted phenol for OCR and Edexcel, right? Look at this. What page is it? This is probably like some copyright infringement that I'm doing, but it's all good. Here you go. You're just gonna have to screenshot this. There you go. So OCR, I think that's your phenol reactions. Screenshot this. This is CGP revision guide. Anyone that's asking, yeah, this is CGP's revision guide. This is the OCR book. And I've got Edexcel's one as well. Edexcel, you only got one reaction though. The front cover, yeah, I'll show you the front cover. Everyone screenshotted that. That's what the front cover looks like. Bad Boy CGP book, the one and only. These are the best books ever. So yeah, that was OCR. And then I'll show you Edexcel's one as well. You've got one reaction of phenol and Edexcel, if I remember rightly. And you see these tables that I was showing you guys earlier with functional group. There you go. Even practical stuff, I don't know how many of you are still in here, but even practical stuff, what I was telling you guys about your approach to chemistry stands with that as well. So me, definitely, when I was in uni, when I was in A-level and I had a practical to do, I used to just do it because I was told to do it. And I would never think about what I was doing or why I was doing it. I'd just be like, oh, okay, the instructions say mix it, so I'll mix it. Don't do that. Think about why the instructions tell you to mix it. Why do you have to heat it up? Why do you have to do all of these things? If you keep asking why, there will always be an answer. And luckily for us in chemistry, the answer is pretty much always logical because atoms are predictable and they're negative on the outside and positive on the inside. And positive things are attracted to negative things. So pretty much everything kind of works like that all the time. And yeah. That's about it. All right, I'm going now. Have you not got any more actual chemistry related questions? Man said she's bare moti. You can tell by the voice. Does that mean motivated? Are you not talking about me? I am bare moti. If is that new? Is that what you kids say? Yeah. Have you got any other actual chemistry related questions before I leave? Miss, what's the outfit of the day? Barbie pajama bottoms and a vest. Skincare secrets, Korean stuff. My ethnicity, I'm a Nigerian and I'm also British and I'm also from St. Kitts in the Caribbean. Access the recordings after this. I'm not sure yet. I haven't really worked that out. Can you do the whole synthetic route for OCR on the revision guide? That's what I sent you lot in a file. When's the next Zoom? I don't know. Oh my Niger, yeah. But no, I'm not. We're not getting into all of that. Maybe I'll do like some get to know me video on TikTok. Thank you so much for coming, guys. I really hope that what I've told you today has actually been useful. Like I said, I know I haven't gone through every single reaction. I'm not just going to explain everything for you. What I'm trying to equip you guys with is the skills so that you can actually understand this stuff and start working it out for yourself. The things that I'm telling you here, as much as they're good, fair and lovely, as much as they're good, I forgot what I was saying now. Yeah, the skills that you're using, they're good in chemistry, but you can use them in all parts of life as well. So it's not just about chemistry. Anytime you get presented with a big problem, break that problem down into lots of small problems and it's manageable. Another really important thing, like I said, is don't force yourself to do this from memory. The most important thing is that you understand. Once you've understood it, then you can worry about doing it off by heart and doing it quickly. But yeah, just don't rush yourself to do things from in exam conditions. Take your time, and if you get stuck on something, send me a message and I will reply to it. I put my email in the chat somewhere. I put the synthesis stuff. I'm gonna make more videos and I'm gonna put more sessions on. Wait a minute so I can download the doc. I will. I'm gonna put more sessions and I'm gonna just do more stuff to help you lot, basically.
No. Can you send the file again?
Can I send the file again? Yeah, I'll send them all. Oh, that's not what I wanted. Oh, just took a screenshot by accident. That's not what I wanted. How do I stop that? File from my computer. I'm gonna put all of them. Reaction types. Oh, hold on. Oh no, that's not it. Hold on. AQA, EdXL, OCR, reaction types. Functional groups. My computer's bugging out. And mechanism summary. But yeah, as I said, if there's any mistakes in there, I'm sorry. And if you see them, let me know. Because I'm only human. All right, is everyone that needs the files got the files? I feel like a real teacher right now. Everyone got what they need. Can I go? Yeah? Yeah?
Thank you.
Bye. You're welcome, guys. It's been a pleasure. Stay posted, keep looking on my TikTok and I'll let you know when I'm doing more stuff.
Thank you.
You're welcome. All the best, guys. Good luck. See you. Bye.